Let's continue, okay? Let's go. So now let me introduce Cathy Swaenepoel, okay, from IMG PRG, Université Paris Cité. She will talk about reversible primes. Okay.
Thank you very much for the introduction, and I want to thank the organizers for the invitation. It's my first time in Rio. I'm very happy to be here. So I'm going to speak about reversible primes. It's a joint work with Cécile Dartige from Nancy, Bruno Martin from Calais, Joël Riva from Marseille, and Igor Spansky from Australia. Okay. So given an integer b larger than or equal to 2, any positive integer k can be written in base b in this way, so with its digits. So here, for each j, epsilon j of k denotes the digit of k at the position j. It's an integer between 0 and b minus 1. And also, so the leftmost digit, the one at the position n minus 1, is not 0. So on the one hand, we can represent an integer by its digits in a given base. And on the other hand, we also have its multiplicative representation as a product of prime factors. And the study between these two representations, also the study of their independence, leads to many interesting and challenging problems. One way to study this independence is to study the digits of some interesting integers, such as prime numbers. The digits of primes have attracted a great interest, especially over the last 2 decades. So I mentioned here only a few results. I start with a result by Christian Maudu and Joël Riva, published in 2010. So here they studied the sum of digits of primes, and they proved that it is well distributed modulo m. So for instance, if you take the base 10 and m equal to 2, they prove that the number of primes up to x such that the sum of digits of p in base 10 is even, so say 0 mod 2 is, so the total number of primes up to x, pi of x, divided by 2 times 1 plus little o of 1, as x tends to infinity. So the same for if I replace 0 by 1, of course. Okay, so by proving this, they solved a conjecture made by Gelfond in 1968. Then I want to mention a result by James Maynard, published in 2019. So he studied primes with missing digits. In particular, he proved that there are infinitely many primes with no digit 7 in their base 10 expansion. And more precisely, he obtained an upper bound and a lower bound of the correct order of magnitude for the number of primes up to x with no digit 7, say, in base 10. Then I want to mention a result by Jean Bourgain from 2015. This was for the base 2, and then by myself for any base, regarding primes with prescribed digits. So I just come back. So we choose a set of positions, j, for the digits, so a set of integers between 0 and n minus 1. And at each of these positions, at each j in this set, we prescribe the value of the digit. So we want the digit at this position to be equal to some value. And the question is, how many primes are there with these digits at these positions? So we obtained an asymptotic formula as the total number of digits n goes to infinity. And we were able to prescribe a lot of digits. Precisely, we could prescribe a positive proportion of the digits and still get an asymptotic formula. Then I mentioned a result which is maybe less frequently mentioned. So this is a result by Bruno Martin, Christian Maudu, and Joël Riva, where they study primes which are called in French équilibrés in a given base. So I give an example here. So in base 2, 8 is 3. It's a prime. Its base 2 expansion is 1, 0, 1, 0, 0, 1, 1. So in base 2, there are two possible values for the digits, 0 and 1. And if you count the number of zeros here, and if you count the number of ones, so you don't get exactly the same results, but they're very close. They differ from at most 1. So in this case, we say that this number is équilibré in base 2. And this definition can be generalized to any base. And so they obtained an asymptotic formula for the number of primes which are équilibrés in base B up to x, as x goes to infinity. And finally, I wanted to mention a result which is less recent, but more connected to what I'm going to present today. So this is a result by Sylvain Coll about palindromic primes. So the palindromes are very rare. There are very few palindromes. So studying palindromic primes is probably very difficult. Nevertheless, we can expect results in this direction. So Sylvain Coll obtained an upper bound for the number of palindromic primes up to x, which is very good because it is of the expected order of magnitude. And then, so he did not prove that there are infinitely many palindromic primes, which is probably very difficult. But he was able to prove that there are infinitely many, so this is in base 2, infinitely many binary palindromes, which are almost prime. By almost prime here, I mean an integer k with at most 60 prime factors counted with multiplicity. So this 60 here corresponds to the base 2, but actually he obtained the result in any base. And this result has been improved very recently by Toxanidi and Panario. So they proved that this 60 can be replaced just by 6. So there are infinitely many palindromic almost primes, where almost prime means with at most 6 prime factors. Okay. So now I need to define the reverse of an integer k. So given an integer k written like this in base B, we define its reverse by this quantity. So the reverse of k is denoted by k with an arrow like this. So it's the integer that we obtain from k by reading its digits in the other direction. So for instance, in base 2, if we take 23, so its digits in base 2 are 1, 0, 1, 1, 1. So the digits of its reverse in base 2 are 1, 1, 1, 0, 1. And so it's 29. Okay. So with my co-authors, we decided to focus to the base 2, which is an emblematic case. So from now on, the base is 2. So the quantity we're interested in is so this one, theta of n, which is the number of integers a with n bits, such that a and its reverse are prime. We want both of them to be prime. So such an integer a is called a reversible prime because it is a prime, and when we read its digits in the other direction, we still get a prime number. Okay. So for instance, for n equal to 5, so we are here between 16 and 32. The first prime is 17. Its digits in base 2 are 1, 0, 0, 0, 1. So actually, it's a palindrome in base 2. Okay. Next prime is 19, but the reverse of 19 in base 2 is 25. It's not a prime. Next prime is 23. So we saw that its reverse in base 2 is 29, which is a prime. Okay. Next prime is 29. Its reverse is 23. Okay, it's a prime. And next prime is 31, which is also a palindrome in base 2. Okay, so the number of 5-bit reversible primes is 4, and this includes 2 palindromes. So the problem we're interested in is to estimate theta of n as n goes to infinity. So what's the expected quantity So this should be, so the total number of integers a between 2 to the power n minus 1 and 2 to the n, so 2 to the n minus 1, times the probability that a and its reverse are prime. At first sight, the event a is prime and the reverse of a is prime can be seen as independent events. So this probability should be the product of the two probabilities, and the probability that a is prime is about 1 over log of 2 to the n. And so the same for the second one, so we get a square. OK, so at first sight, we expect this. Actually, we will see that the two events, a is prime and the reverse of a is prime, are not really independent. So we don't expect exactly this, but almost. So for the moment, I state the conjecture in this way. So we expect that theta of n is equivalent to 2 to the n divided by n squared times some constant c, some positive constant c. OK, and so at the end of my talk, I will give a more precise conjecture on this with an explicit value for c. OK. So with my co-authors, we studied this problem. And here is our first result. So we introduce the set Bn just for convenience. So this is the set of all n-bit integers a, which are odd. This set is very convenient because so in base 2, this means that the digit at the position n minus 1 is 1, and this means that the digit at the position 0 is 1. So when you take the reverse, this is still the case. So we have this stability here, which is quite convenient. OK. And then, so we study the quantity, instead of studying directly the quantity theta of n, we study theta of n and z, which is the number of a in our set Bn, such that all prime factors of a and its reverse are larger than z. So here, p minus denotes the smallest prime factor. OK. So in the papers I mentioned in the introduction by Sylvain Cole and by Texandi and Panayo about palindromic primes and palindromic almost primes, the author developed an approach based on a linear sieve, essentially. In our case, this is not suitable, just because the problem is different. Nevertheless, by developing an approach based on a two-dimensional sieve, we prove the following. So we can prove that if z is of the form 2 to the power gamma n, then we have this upper bound. So theta of nz is at most a constant, which may depend on gamma, times 2 to the n over n squared. And this is for any gamma between 0 and 1. So this is for the upper bound. We also get a lower bound. So we prove that for sufficiently large n, this is also larger than some constant times 2 to the n over n squared. But here, for the lower bound, theta is in a smaller interval. It has to be less than 1 over 2 beta 2, which is an absolute constant. This is about 0.117. I say a few words later about this constant beta 2 here. OK, so this is for theta of nz. Now, what can we deduce? So first, we know that the quantity we're interested in, theta of n, is less than theta of nz. Because if a and its reverse are primes, then the prime factors of a times its reverse are a and its reverse, which are both larger than 2 to the n minus 1, so larger than z, as soon as z is like this. Okay, so from the first part of the theorem, so from the upper bound, we can deduce this. So theta of n is at most a constant, absolute constant, times 2 to the n over n squared. Which is good because 2 to the n over n squared is the expected order of magnitude for theta of n. Okay. So we note that if A is less than 2 to the n, and all its prime factors are larger than 2 to the power gamma n, then A cannot have too many prime factors. More precisely, its number of prime factors counted with multiplicity is less than 1 over gamma. Okay, and in the second part of the theorem, for the lower bound, our limit for 1 over gamma is 2 beta 2, which is about a bit more than 8. So it follows from the second part of the theorem, the lower bound for theta of nz, that the number of integers a, such that a and its reverse have at most 8 prime factors, is at least some constant times 2 to the n over n squared. So this gives a good lower bound for the number of n-bit reversible almost primes, where almost prime here means with at most 8 prime factors. So I said that this is a good lower bound because 2 to the n over n squared is not the expected size exactly for this quantity. There's just some power of log n missing, which is due to the fact that the almost prime that we detect here with our method do not have small prime factors. Okay. And also, as the techniques that we develop, as an application of the techniques that we developed to prove the first theorem, we can deduce, so we obtain this asymptotic formula so for the number of integers a in Bn such that both a and its reverse are square-free numbers. So we obtain the cardinality of the set Bn, okay, times, so this constant. So the probability that an integer is square-free is about 6 over pi squared. So at first sight, we would expect a constant here, which is 6 over pi squared. So 36 over pi to the 4. We don't get 36, we get 66. Okay, so the fact that we don't get 36 exactly is not very surprising because the events A is square-free and the reverse of A is square-free are not really independent. There are some dependencies. So in our paper, we take into account these dependencies to explain why actually the constant we expect is exactly this one, not 36 over pi to the 4, but this one. Okay. So now I'm going to give you some details about the proof of the first theorem to the lower bound and the upper bound for this quantity. Okay, so we want to estimate theta of nz, which counts the number of integers a in Bn, such that all prime factors of a and its reverse are larger than z. So in other words, such that a times its reverse is co-prime to p of z, where p of z is the product of all primes up to p. And since a and its reverse are both odd numbers, we can start here at 3. Okay, so theta of nz is what we call the shifting function for this sequence. Okay, so if we have some information about this sequence, then by using some shift techniques, we can expect to obtain some estimates for the shifting function. What kind of information do we need about the sequence A? We need a good approximation for the number of terms of the sequence which are divisible by d. We need only this on average over d. So we will see that in our case, indeed, we can prove such a good approximation. I will give a precise statement. This will be lemma 5. Once we have this good approximation, we apply a two-dimensional sieve, more precisely a result by Diamond, Halberstam, and Richard from 1988. And we obtain the theorem 1, the upper bound and the lower bound for theta of nz. So in the second part of the theorem 1 for the lower bound, so the exponent gamma could not be too large. It has to be less than 1 over 2 beta 2. So this constant beta 2 here is associated to the sieve we use. So it appears in this paper, and it is called the sieving limit. Okay. So now I'm not going to give you details about the sieve we use. I'm not going to explain how we deduce theorem 1, but I want to spend some time on this part, which is the crucial part. So what good approximation exactly do we obtain and how? Okay, so we are interested in the quantity Tn of d, which counts the number of integers a in Bn such that d divides a times its reverse. Okay, so we want a good approximation for this on average over d. And we only need to consider integers d which are square free and odd. Okay, so first, heuristically, what do we expect? So we take an integer a at random in Bn. What should be the probability that p divides a times its reverse? So to start, we can take for d a prime number. Okay, so look at the probability that p divides a times its reverse. So this is the probability that p divides a or its reverse. So the probability that p divides a plus the probability that p divides the reverse of a minus the probability that p divides a and its reverse. Okay, these two probabilities are 1 over p, okay? And for this one, so the evens p divides a and p divides the reverse of a can be seen as independent evens. So we obtain a 1 over p squared. So finally, for the probability that p divides a times its reverse, we obtain about 2p minus 1 over p squared. Okay, so I wrote here for p larger than 5, because actually p equal to 3 is special. So for p equal to 3, actually the two evens, p divides a and p divides the reverse of a, are not at all independent. Why? Because modulo 3, we have this relation between a and its reverse. This comes from the definition of the reverse, modulo 3, directly. So in particular, a is divisible by 3 if and only if its reverse is divisible by 3. So the probability that 3 divides a times its reverse is just the probability that 3 divides a, so 1/3. Okay? Now, if for d we take a product of two distinct primes, p1 and p2, so the probability that p1, p2 divides a times its reverse is the probability that p1 divides a times its reverse and p2 divides a times its reverse. These two independents can be seen as independent evens. So we expect to obtain the product of the two probabilities. Okay, so finally, for the probability that D divides the A times its reverse, we expect this. So this should be about f of D divided by D, where f of D is a multiplicative function whose values at primes are given here. So for p equal to 3, f of p is 1, so that we get here 1/3. For p larger than 5, this is 2p minus 1 over p, so that we get this here. Okay, and if p is equal to 2, or if we have a prime power here with nu larger than 2, we just put the value 0 to define properly the function f. Okay, so we expect this probability to be f of d divided by d. So we expect Tn of d to be about the coordinate of the set Bn times this. Okay, so we expect, in other words, that this difference, denoted by Rn of d, is small. Okay, and indeed, we can prove that it is small on average. So here is the precise statement. This is our main technical result. So here we sum over all d, odd and square free, up to some bound. We sum, so the absolute value of Rn of d. There's a factor here, just because the quantity we need to bound to apply the sieve after is exactly this one with this factor, okay? So we sum over all d up to 2 to the power psi n. And psi can be chosen arbitrarily close to 1/2. Okay, and so we prove that there is a constancy so that we have this upper bound here. And to obtain the theorem 1 by applying a sieve method, by using a sieve technique, we need this to be a little o of 2 to the n divided by n squared. So, okay, perfect. Okay, and so the fact that we can go for psi, for the exponent here, up to 1/2 means that we have a level of distribution which is 1/2 here. Okay, so I'm going to give you some details about the proof of this main technical result. So we want to show that this quantity, so the difference between Tn of d and its expected value, is small, on average over d. Okay, so we need an expression of Rn of d we can work with. So we use exponential sums. So Tn of d is this quantity, so the sum over all a in Bn, such that a times its reverse is congruent to 0 mod d of 1. Okay, so we start by rewriting this in the following way. So we filter according to the value of a mod d and the reverse of a mod d. So this gives a sum over all uv, such that uv is congruent to 0 mod d. Have the sum over a, and a quantity which is 1 if a is u mod d and 0 otherwise, times a quantity which is 1 if the reverse of a is v mod d and 0 otherwise. Okay, then, so we have two congruences. We use the orthogonality relations for additive characters to detect them. So this gives this quantity. So now we detect this congruence with this exponential sum over h1, and this one with this exponential sum over h2. Then we change the order of summation. We put the summation over h1 and h2 outside. And we get this. So with inside the sum over uv and the sum over a, in which there's the reverse of a, which appears. Okay. So now what's the contribution of the pair h1, h2 equal to 0 here? So for this pair, these two exponential sums here are equal to the length of the sum. So the sum here is, so its length is the coordinate of Bn. And so for this one, actually it's not very difficult to see that so divided by d squared, we get exactly f of d divided by d for the same function f, multiplicative function f that I introduced before. Actually, this is true only if d is not divisible by 3. If d is divisible by 3, we adapt the argument. OK. So this quantity here is the expected value for Tn of d. So this means that our Rn of d, which is the difference between Tn of d and this, is this quantity where we remove the pair h1, h2 equal to 0. So this is the expression of Rn of d we use. OK. So we want to prove that Rn of d is small on average over d. So we have to handle these two exponential sums. This one is not very difficult to handle. But for this one, in which there's the reverse of A, there's some work to do. So since this exponential sum is very important, we introduce a notation for it. So we denote by f, capital F sub n of alpha and theta, so this exponential sum, and we normalize with this factor. So with this notation, the sum in blue here is equal to the coordinate of Bn times our function Fn evaluated at h2 over d and minus h1 over d. So to prove the lemma 5, our main technical result, we need to prove essentially two kinds of bounds regarding these values. OK, so first bound, this can be seen as a pointwise bound. So one of the two arguments is of the form h over d, with some natural conditions on h over d. For instance, we don't want it to be equal to 0. So we prove that for any alpha, this is at most, so this quantity, which depends on n, the index here, and on the denominator d. OK, so if d is, so I should say that the trivial bound for this quantity is 1. So if d is small, so if the denominator is small, OK, perfect. This says that this quantity are small. But we need to be able to handle very large denominators. Our denominators d can be some powers of 2 to the n. So for such denominators d, so very large, this is essentially a constant. So this upper bound is nothing for very large denominators. So we need another argument. So we prove an upper bound for this more complicated quantity, but so here we look at the values of our function fn evaluated at two irreducible fractions. Okay, so there are many variables, but we sum over all the variables. So the denominators, d1, d2, d3, here. Each di is of size big Di. And we sum also over the numerators, so h1 and h2, such that these fractions are irreducible. OK. So we prove that if the denominators are not too large, precisely if big D1, big D2, big D3 is less than 2 to the power xi n, for the same xi as in the lemma, so xi can be arbitrarily close to 1/2, we have this a sufficiently good upper bound. OK. So now I'm going to give you some arguments to prove these two bounds. So I recall the definition of our function fn here. The first argument is a product formula. So as in many problems regarding digits, we have a function in which there's information about the digits, and we can rewrite this function as a product, and then we take advantage of this product representation. So how do we obtain this formula? So we have a sum here over all A in Bn. So we write A in base 2, and so also its reverse. Okay? So summing over A is summing over all the possible values for the digits. And it's not very difficult to see that when you write this, you can you obtain very quickly this formula. So in absolute value, Fn of alpha and theta is a product of some, so here some function u, but this is just a cosine, of some, so not very simple quantity, which depends on alpha and theta and some powers of 2. Okay. So next argument, we prove a bound for this quantity, which is uniform in alpha. So this does not seem very simple because in this formula here, so we have a product over j, and for each term j, the term, so in this term we have alpha which appears, theta also. So getting a bound which is uniform in alpha does not seem very easy. But by grouping judiciously the terms in this product, we can remove alpha without losing too much. So since this is very, the proof is very short, I can give you the proof. So how do we group the terms of the product? So we look at the cube of Fn of alpha and theta. So now for each j, we have 3 copies of the term corresponding to j. Okay, so how do we group these terms, all these terms? So for each j, we take 1 copy of the term corresponding to j. This is this u. And 2 copies of the term corresponding to j plus 1, the next one. This is this term. Okay. So we get this upper bound. And then, so here what we have is something of the form u of x times u squared of y. And from this definition of u, it's not very difficult to see that we have this upper bound which depends on x minus 2y. Okay, so our x is this quantity, our y is this quantity. If you compute x minus 2y, the alpha disappears. And so we get this upper bound here, which depends now only on theta. Okay, so we have a bound which is uniform in alpha. So to prove the first lemma, so the pointwise bound, we just need to take for theta h over d. And we want to prove so that this quantity with theta equal to h over d is small. Okay, how do we do this? We just prove that some terms of the product are small. All the other terms are bounded trivially by 1. So this is now quite classical. And so by doing this, we obtain the bound I stated for, so the bound I stated in lemma 6, the pointwise bound. Okay, so the pointwise bound is not so hard to obtain. For the second bound on average, things are more difficult. So we need more arguments. We use the Cauchy-Schwarz inequality, okay? And then we need to bound these 2 quantities here. So first one, we have the square, because we had applied Cauchy-Schwarz before. Okay, of the absolute value of Fm. So here this is m, not n. M is less than n and well chosen. And we evaluated that, again, two irreducible fractions. But here we don't sum over all the variables which appear here. We just sum over D1 and H2. So D1 and H2. All the other ones are fixed. OK. So the points H2 over D1, D3 are actually well-spaced modulo 1. And we control the spacing. This is this. OK. This is a trigonometric polynomial, so we can apply the large sieve inequality, which gives this upper bound here. So of course, we apply this with a good choice of m, depending on the size of D1. And then, so we have all the other variables that we had fixed here, so D3, H1, and H2 to handle also. We handle them here, so in this quantity here, so we sum over D2, D3, and H1. We have again the square of some FL and so the irreducible fraction H1 over D2, D3. Okay, but now compared to here, we have a max over alpha. Okay. So we saw that this was the second argument. We have a uniform bound for FL, bound uniform in alpha. So we have an explicit upper bound for this maximum, depending on H1 divided by D2, D3. And so the points H1 over D2, D3 are again well-spaced, modulo 1. And we control the spacing. So we can apply the Sobolev-Gallagher inequality to bound this quantity. This makes appear some L1 norms. But here in our case, we have a very good control on these L1 norms. So this is fine. OK. So by combining all these arguments, we prove the two bounds, the pointwise bound and the bound on average. And from these two bounds, we prove our main technical result, the lemma 5, which says that Rn of D is small on average over D. OK, so as I said at the beginning, I want to give a more precise conjecture on theta of n. So theta of n, which is so the number. So theta of n is so the number of A in Bn such that A is prime and its reverse is prime. OK. So what do we expect more precisely for theta of n? So we take an integer A in Bn at random. We look at the probability that A is prime, and the reverse of A is prime. So as I said at the beginning, and so these two events are not expected to be independent. Why? Because modulo 3, for instance, so A is not divisible by 3 if and only if the reverse of A is not divisible by 3. So we have this dependence to take into account. So these two events are not expected to be independent, but given that A is not divisible by 3, which is equivalent to the reverse of A is not divisible by 3, we expect these two events to be independent. So we expect this to be the product of the two probabilities. Probability that the reverse of A is prime, given that 3 is not divisible by A, which is equivalent to the reverse of A is not divisible by 3. Okay. So now what's this probability? So this is the probability that A is prime divided by the probability that 3 does not divide A. And for this one, this is the same, they are equal. So we get a square. Okay, so now the probability we are interested in is the probability that A is prime and the reverse of A is prime. So this is this probability times the probability that A is not divisible by 3. So we get the probability that A is prime squared divided by the probability that A is not divisible by 3. Okay. What's these probabilities? So the probability that A is prime, have to be careful. A is taken randomly in the set Bn, which is a set of odd integers. So the probability that probability that A is prime is about 2 over log of 2 to the n squared. Probability that A is not divisible by 3 is 2/3. So we get log of 2 to the n squared 2 times 3. Okay. So finally, theta of n is expected to be about the coordinate of Bn, which is 2 to the power n minus 2 times this. So 2 to the power n minus 2 times this gives, so theta of n should be about 2 to the n minus 1 divided by log of 2 to the n squared. Okay, so this is our conjecture. Okay. And so to express this probability here that A is prime, if you use the Li function, so you get here this exactly this quantity theta exp of n, which is of course equivalent to what I said. So. Okay, so this is our conjecture, and this agrees with the value of theta of n that we could compute. So we could compute the values of theta of n for n up to 50. So this took some time because, for instance, for n equal to 50, so we need to compute the number of 50-bit reversible primes, and 2 to the power 50 is about 10 to the power 16, so quite large. Okay, so if we plot theta of n divided by what we expect, theta exp of n, we should observe a convergence to 1, according to the conjecture. And indeed, this seems to converge to 1. So the conjecture really agrees with the values of theta of n. Okay, so to conclude, with a sieve argument, we obtain first an upper bound, which is good because it has the expected order of magnitude for the number of n-bit reversible primes, so theta of n. We obtain a lower bound for the number of n-bit reversible almost primes, where here almost primes means with at most 8 prime factors. And we obtain an asymptotic formula for the number of n-bit reversible square-free integers. Okay, I stop here. Thank you very much.